Welcome back to more Calculus 2 practice problems. Today we are doing volume with the cylindrical shell method. So the cylindrical shell method is a thin cylindrical shell inside a shape that you can unfold, right? You can pretend it's like a piece of paper all folded up in a cylindrical shell. You can unfold it, right? So the cylindrical shell has some width, delta x, right? And that will be the width of this paper, a very thin change in x, a very thin, just like a piece of paper, right? And the entire top of that paper all folded up, when you unfold it, just becomes the length of this rectangular prism, right? So 2 pi r is the length we're giving this rectangular prism, where r is really a function of x, because as the cylindrical shell moves outwards, its r increases, right? And we also have some function height of x. Well, in this picture right here, right, the height is constant, so the height of all these shells is the same. We would be able to pull it out of the integral. But in general, when you have a shape like this that revolves around and makes another shape, it will not have a constant height, so we will have to leave it inside the integral. But basically, we can find the volume of this rectangular prism. It's going to be the length of the prism times the height times the width, right? So that is the delta volume, the volume of one slice. And we are going to take the limit as n approaches infinity. N is the number of rectangles, or cylindrical shells, right? By taking the limit as n approaches infinity and adding them all up, this here is all delta v, we are essentially just integrating, and that delta x is going to turn to that dx. So we can pull the 2 pi and out of the integral, leaving just those radius and height functions inside. So this is now our third method of finding volume. Remember, we also know the disk and shell method. So let's look at an example. Prove that the volume of a cylinder is pi r squared h using the shell method. So if we unfold this cylinder onto a Cartesian plane, it leaves us with this rectangle, right? If we revolve that around this axis, we would get that cylinder, right? And you can see what happens to this blue slice right here when it gets revolved around. It turns into this cylindrical shell, hence why it is called the cylindrical shell method. So we just proved y, but you don't really need to know y. All you need to know is the formula, 2 pi r of x, h of x dx. So we need to find r of x, we need to find h of x. So r of x is basically all of these different slices have some radius. What is the function that represents that radius? Whenever you're revolving around the x-axis, it's just x. Here's why. When you're at this x value, what's the radius? Just that, right? And when you're at this value, this is the radius. So it is exactly proportional. Whatever x value this slice is at, like for example, this value, call it x. If you go straight down into the function, you can see that the radius, if I drew it correctly, the radius of that shell would match up exactly with the picture we drew here. So the function x just represents the radius. In summary, like when we're here at the origin, you can see that the radius of the shell at the origin is 0, which is why at x equals 0, there's an r of 0. But when we're at this radius, or I should say at this x value r, we're at the entire radius of r. So x is just the r of x function. The h of x function, in this case only, we know how to do this. What is the displacement between this function and this function? So that would be y equals h minus y equals 0. We're just going to get a constant h in this case only. So the volume of this cylinder is 2 pi. Those slices are dx values, right? So we better have x values as our bounds. They're moving all the way inside from 0 to that radius r. They're moving from here to here. And we have our r of x function and our h of x function and our dx. The h is a constant, we can pull it out, 2 pi h. So we're just integrating x dx. That'll give us 1/2 x squared. And we're going to evaluate that at r and 0. So volume equals 2 pi h 1/2 r squared. Well, let's see. The 2 and the 1/2 cancel. And we are left with pi r squared h, just like we know the formula to be. So we proved the volume of a cylinder already using the disk method in the last or a couple videos ago, and now we have proved it using the shell method. So let's look at this example. Here's a pretty basic example, and I want to do it two ways. I want to do it with the shell method and then do it with the washer method. So when we revolve this shape around, we are going to get what kind of solid? Well, you reflect it to the other side. Drawing's not perfect. And then you connect the points like this. So it's all hollow right here in the middle, right? But it is dense or solid, like right here and over here. And it tapers down to here. That's how the shape looks. So anyway, you can see that when we revolve that blue around, when we revolve that vertical slice around, we're going to get some kind of cylindrical shell, like this. So we know that V equals 2 pi r of x and h of x, since we're revolving around the y-axis. The radius function is just x. Whatever x value you're at is the radius of your shell. For example, we're here at x, that radius is just that x, right? Then what is the height function? Well, the height function is represented by the displacement between this function and 0, and that function is just y equals x. So the height function is just x as well, dx. Here's why the height function is just x. What happens at x equals 0? You can see that the height is 0. What happens at x equals, this is 2, and this is 2. What happens at x equals 2 over here? Well, the height of that shell is 2. That's why x is a good height function as well as a radius function. So that we're going from 0 to 2 because the slices are starting here at 0 and ending here at 2. Okay, so V equals 2 pi integral of 0 to 2 x squared dx. So V equals 2 pi 1/3 x cubed. 2 and 0. V equals 8/3 times 2 pi, or 16 pi over 3, right? So that is how you do it with the shell method. But I also want to show it with the washer method. So now look at this yellow slice here. If we were to revolve that one around, it would come over to here, and then when you connect all the points, you kind of get this washer shape, right? If I drew it neater, you'd be able to tell more. But you can see it's like a disc without this inner disc here. So we know what this is just review from last time, but we know that the washer method is pi big R squared. Well, what is big R? Big R is going all the way from here to here. It is constant. Big R is a constant 2, because when we're at this slice all the way at the bottom, the big R is 2 as well as at the top, but the little r is changing, right? It's small here, but it's big over here, and now this picture is getting very messy. But what is little r? It's the displacement between this function and this function, right? We know that that function is y minus 0. See how we changed it from y equals x to now x equals y? We want that to be y because with the radius, or with the washer method, we have a dy. So with the washer method, we have big R squared minus little r squared. So volume equals pi. And what are we going from and to? Well, we're starting at this y value, and we're going up all the way to 2, if I drew it correctly. So 0 to 2. Big R squared is 4. Little r squared is y squared. And dy. So v equals pi 4y minus 1/3 y cubed. Evaluated at 2 and 0. That's going to give us pi out of 8 minus 8/3. Well, 8 is the same thing as 24/3 minus 8/3. So v equals 16/3 pi. So good thing that we got the same answer, right? So you can choose which one you like better. Here's why it will be more beneficial to do one or the other. We'll look at in the next answer. Personally, I like to use the shell method better because usually this one is always x, and if it's not x, it's pretty easy to figure out what it is. But sometimes finding the big R and little r here can get tricky, so I like to stick with the shell method personally. But let's look at this problem. If you watched my last video, this problem should look familiar. We're going to do this one as well. Okay, here is why it's beneficial to use the shell method. We did this one with the washer method in the last video, and it took 15 minutes. It was a pretty bad integral, but this one is going to be much, much quicker with the shell method for 2 reasons. One, we only have one kind of displacement going from this function to this function, whereas when we had the horizontal slices, we had 2 kind of displacements, because right here something happens. Instead of going from this function to 0, we went from this function to 0. So we had to have 2 integrals, one to account for this and one to account for the other one, or above that. Here's the second reason why a shell method's easier. We already have this as a function of x, which means we typically would want a dx, because remember, in the integral, when you have a dx, this has to be x values. So doing the washer method, we had to solve this for y. So and sometimes that can be tricky. Like, what if this was a 6x plus 3? Now it's impossible to solve for y. So you would have to use the shell method in this case. Of course, the shape would change, but so really you're going to base the method you want to use off of the function. If it's already solved in terms of x, you want to use a dx. And whether that's a washer method or a shell method depends on the axis you're revolving around. Because in order to make this shell, in order for this blue slice to appear over here, it has to be parallel to the axis you're revolving around. So with the shell method, it's always parallel to the axis you revolve around. Okay, so let's look at now. Let's draw the shape over here. When we reflect it, it should look something like this. Not perfect, but it'll work, right? And then this comes over here, this comes over here, this comes over here, and here, and this comes over here, this comes over here. So it's not perfect, but it'll work. This is all hollow in the middle. This is all hollow, and it's solid on the other sides. Do you see why a shell method might be a bit better? Let's see. I'm not going to deal with this rectangle. I think we got it good already. We can just go straight for the volume is 2 pi integral. Where do these slices move from, or to and from? They move from here all the way to here, but they didn't give us that x value. But notice it's the x value where they intercept. So where does minus x squared plus 6 intercept x? Or where do they equal each other? Well, x squared plus x minus 6 equals 0. So we have x plus 3 and x minus 2. So these two functions intercept each other left of the y-axis at -3 and to the right of the y-axis, which is where we are at 2. That tells me that the y value here is 2. The other way we could have done it is, if this is 2 and this is y equals x, this must be 2. Right? That's the easy way. But this is a good habit to get into for some tougher ones. So we know we're integrating from 0 to 2. Now we just need a height function and a radius function. So the height function is just the displacement between the two functions. And because it's the same slice, what I mean by the same slice is this slice right here is going to be the same as this one and the same as this one. Just the displacement between this function and this function. So what is that top function? Minus x squared plus 6 minus the bottom function x, right? So that is our height function. The radius function, we are not revolving around the y-axis anymore. So now it's not going to be just x, but it's going to be something similar. So I'm going to put it out there. It's going to be 4 minus x, because we're starting here at 4 and we're moving, the radius of these shells is moving in the negative x direction. And we can prove that this is correct. Let's prove this is correct. R of x is equal to 4 minus x. Let's see, what happens when x equals 0? That means you would have r equal 4. Is that true? When we're here at 0, do these shells that are at 0 really have a radius of 4? Well, yes, because they are here and they get reflected to here, and those shells have a radius here of 4. Okay, let's try another value. What happens when x equals 4? According to our function, it should have a radius of 0. That means all these slices, right, the ones here at 4 will have a radius of 0. That is correct, because when we revolve this, the one in the very middle of the shape, it would have a radius of 0 because it has nothing to go around. Either way, though, we're not concerned about any rectangles to the right of this x equals 2 spot. But we can still use other values to the right of it to check that our radius function is correct. So now the radius function is either going to be one of two things. It's either going to be x or the number that you're revolving around minus x. That's, of course, when you're revolving vertically. If you're revolving like this way, for example, about the x-axis, it would just be y and then some number minus y instead. Okay, so that tells me that the volume is 4 minus x, and then we have minus x squared plus 6 minus x dx. So this might look like a tough integral, but it's really not. So let's distribute. We can distribute this 4 to this term, and this term, and then the negative x to this term, and this term. And trust me, this is going to be a lot better than the alternative. So we have a negative 4x squared, and a positive 24, and a negative 4x from the first 4. And then when we distribute that negative x, we're going to get a positive x cubed, and a negative 6x, and a positive x squared. Right? Yes, we have a dx. Let's combine some like terms. We can combine this negative 4x squared and this positive x squared to make a negative 3x squared. We can combine this negative 4x and this negative 6x to make a negative 10x. We can combine this positive 24 with nothing, and this x cubed with nothing. Right, and dx, so volume is going to be 2 pi. When we integrate it, it's going to be negative x cubed minus 5x squared plus 1/3 x cubed plus 24. Evaluating that at 2, or 24x. Evaluating that at 2 and 0. V equals 2 pi, negative 8, negative 20, plus 8/3. This should be integrating x cubed would leave you with 1/4 x to the 4th. Hopefully you caught that mistake. And when you plug in 2 to the 4th power over 2 to the 2nd power, that is going to leave you with 2 squared, or 4. 24 times 2 is 48. Finally, this leaves us with, let's see, 2 pi times, we have a negative 28 and a positive 48, which make a 20, and a 4. So 24 times 2 pi equals 48 pi. So that one was pretty rough, right? But it didn't take us 15 minutes. It maybe took us half of that. It took us 15 minutes to do it with the washer method, which I copied in right here. So doing it with the washer method, we had to do it with 2 separate integrals, and we had to solve this function for x equals. Then we had to do the 2 separate integrals, and they were pretty tough integrals as well. And our final answer that we got was 144 pi over 3. That's a different number. Oh, no, it's the same number. We could have simplified that to get that 48 pi, right? So, in conclusion, you should be able to do both methods and be able to choose the right one. It was screaming at you by having a function of x and only needing one integral to use the shell method here. That's why this one was so much easier. And but really, this is the only part that's important, is setting up this integral. If you know how to set up this integral, you'll do fine in the other classes, because we can just use our calculator to get all of this stuff. But it's good to know that stuff too. Okay, so now let's look at the last problem. Find the volume of the solid bounded by the equations y equals x squared plus 1, y equals 0, x equals 0, x equals 1 after revolving around the y-axis. And they didn't give us the picture, so we're going to have to draw it. Well, y equals 0 is the x-axis, and x equals 0 is the y-axis. X equals 1 is this line. How about x squared plus 1? Well, it has a y-intercept of 1, and it grows like a x squared. So this is the region that we're talking about. And I want you to revolve it around the y-axis. So should we do shell or disk? Here's why I want to do shell. Because one, we can do it with one integral, because every slice in this interval will just be coming from x squared plus 1 to 0. And they already gave us the radius, or the height or radius function, as a function of x. So it's already set up for us to use a dx, is my point. Could we have done it with a washer method? Yeah, we only need oh no, because we need 2 integrals. This displacement is going from this function to this function, but anything past this, you would need another integral, because now it's a constant displacement. So we would need 2 integrals. So why would we use a washer method here? We'd have to solve this function for x, and we would have to do 2 integrals. This is why the shell method is better in this case. It's going to be 2 pi. The radius function, since we're revolving around x equals 0, is just x. At any given x value, it has that radius. What is the height function? The height function is just the displacement, like I said, between this function and 0. So it's just going to be that function, x squared plus 1 dx. V equals 2 pi. What are we integrating from and to? Well, the slices move all the way from here all the way to here, x equals 1. So they're going from 0 to 1. 0 to 1, x cubed plus x dx. V equals 2 pi. When you integrate x cubed, you get 1/4 x to the 4. When you integrate x, you get 1/2 x squared. Right? And we're going to plug in 1 and 0. We're going to get 2 pi times 1/4 plus 1/2. 1/4 plus 2/4 is 3/4. And we could simplify a little bit to leave us with 3 pi over 2. So I chose this example to show you that the shell method really prevailed over the washer method in this case, because 1, we didn't have to do 2 integrals. 2, it's already given to us as a function of x, so we would want to use a dx slice. Could we have used the washer method? Yes. Would it have been the easiest way to do it? No. So we should know how to do both ways. So that is how we do the shell method. It's really not too bad.